Fecal indicator bacteria assessment is the focus of this video, and we're going to be talking about how we assess drinking water quality and recreational water quality, not just here in the United States, but all over the world. Starting off, I'm showing you a couple pictures that include some of my former students, Ambrose Maritime and Adams Rono up there in the top left. And you can also see below them some of their relatives holding up the EKU bag down there. And I put those kids up there because they're a big reason for why we're doing the work that we're doing. Around the world, reports of about anywhere between 2 and as many as 4.4 billion people do not have access to safe drinking water and sanitation. So that's a major, major problem for preventing the spread of infectious diseases. And CDC and UNICEF, they published a paper that's in the Lancet that shows that about 88% of the world's diarrheal deaths are due to unsafe water and inadequate sanitation. So it's a lot, 88% of all the diarrheal deaths. And if you knew how many diarrheal deaths there were worldwide, you would be troubled by that. So let's just look at the kids, where the diarrheal deaths are the most numerous. 2,200 kids die every day, not like every year, like every day. 2,200 kids under 5 die from diarrheal illness. That is the equivalent of 5 jumbo jets crashing every day full of kids. It's a lot. So we've got our work cut out for us. So we know that these diseases are preventable. We just need to empower communities with the data to be able to advocate as well as respond to the challenging areas of their communities. So you can see up there in the top right corner a couple of my former students, his little brother and his nephew, helping us there with our Colilert plate project. This plate, made in Canada, it runs about $10 a piece. And then down there in the bottom right corner are the faculty at Moy University in the Department of Environmental Health. And then here we are with the Ministry of Public Health and Sanitation. And to this day, we still, that's Mika Koch, we still stay in contact. And here on the right, we've got the faculty at Kisii University in southwest Kenya. They serve a population that's got a few 100,000 people that are connected to a public water system, and they've been advocating for trying to get better resources for enumerating E. coli in their water, along with a lot of other needed resources for their water lab. And we've got groundwater issues and water issues here in the United States too. Here's a picture of a cistern. About 15% of Americans get their water from wells and springs, and there's about 12 to 16 million drinking water illnesses annually in the United States. This particular spring is from Pine Mountain in southeast Kentucky, and people still are going to it, and there were milk caps and stuff around it where people fill up these gallon jugs at night, even though it's labeled "do not drink the water." Not because of the E. coli, but probably because of some of the other things that were going on above that area. So we worry about these problems worldwide because we know that they're also associated with antibiotic resistance development. In areas that don't have sanitation or drinking water infrastructure that's modern, we see the shedding of fecal bacteria that can be either into the ground or onto the surface that then ends up in the drinking water supply. People may wash their hands with it. They're often drinking it without any treatment, which then exposes them to these harmful environmental flora, which could include antibiotic-resistant bacteria, as well as pathogens. And as people get sick with gastrointestinal illnesses like vomiting and diarrhea, there's an increased likelihood that they're going to be treated with antibiotics. So as they are treated with antibiotics, they shed some of the antibiotics in their stool, and they may also discard unused antibiotics into their waste stream, and they may also shed antibiotic-resistant bacteria into their waste. That then ends up going into their drinking water with low levels of antibiotics in the drinking water, as well as antibiotic-resistant flora. Then somebody drinks that, they get sick, and now the old antibiotics don't work. They need to use something better and stronger. And they use something better and stronger, and then the cycle continues on and on and on in what we call a positive feedback loop. very bad. So we need to fix this problem, which is upstream of throwing antibiotics at it. The antibiotics is a short-term solution, but it will catch up with us if we don't address the problem. Now, water quality testing is not something that's unique to just low resource communities around the world in the tropical areas. We have, again, 15% of our population in the United States that's on groundwater, and those are private groundwater sources. We have about 50% of our United States population that actually, gets its water from the ground. But most of those people that get groundwater on public systems, where the public utility gets water from the ground. 15% of our public gets their water from the ground at their home. They're called private systems, and nobody's testing the water, and people don't know how to test the water, and they need resources to pay to have it tested. So we were doing some studies in southeast Kentucky, and the amount of people that wanted their water tested was incredible. And it's just unfortunate that there's no means of them getting their water tested other than paying a lot of money for it. So a lot of people hadn't tested their water for like 10 years. And there's community groups that are also watching out for our nation's rivers and streams. All of our rivers and streams, according to the Clean Water Act, are supposed to be wadeable and fishable. And you can see, like, the Kentucky Watershed Watch folks, and they use some of the tests that I'm going to show here to determine if the rivers are fishable and swimmable. So had we actually had a chance to have the lab, for this, or if you have a chance to ever participate in one of our labs, this is at Owsley Fork Lake, as was just last year, and you can see, how beautiful that lake is. We collected water samples there and then used the Idexx Colilert method to enumerate the amount of E. coli from that lake. Now that lake is actually a drinking water supply for the city of Berea, and it's not too far from the Pinnacles, if you've ever done any hiking there. So with your water sample, you want to have at least 100 milliliters in a sterile container. We will add this powder, which is called the media, and this particular powder or media is called Colilert. That's the powder's name. And you mix this up by inverting this bottle between 30 and 50 times, back and forth, back and forth, back and forth, and then you open this little foil back plastic tray, you open it up and pour the water down in this. It sits onto a little rubber tray insert, and then this goes into a heated tray sealer, and this $5,000 piece of equipment seals this, and then it goes into an incubator for about 22 to 24 hours at 35 degrees Celsius, and you will see yellow colored total coliforms show up, and those that are yellow total coliforms underneath of a long wave UV light, you will see the E. coli grow, because the E. coli are interacting with a specific chemical that's likely in that powder called mug. The E. coli that glow are to be counted using their MPN table for telling us how many E. coli are present. So in this image, you can see some larger wells and this really large well glowing blue. You see none of the small wells glowing. So when we count them, we go 1, 2, 3, 4, 5, 6 glowing. Then we go to the MPN table that's provided with the kit. So on the MPN table, we have the number of large wells here and the number of small wells here. Again, these are the large wells, including that big one, and then these are the small ones. So we have 6 large wells and 0 small wells. Now, there are 48 small wells on this particular, quantity tray. On this slide, you see the front page, which goes all the way up to 24. There's a back page for small wells that goes from when you have 25 to 48 small wells that are positive. Now, in our example, we had 6 large wells and 0 small wells. So we can zoom in on that, and you'll see 6 large wells and 0 small wells, and that gives us 6.3 E. coli per 100 milliliters. So these results are per 100 milliliters, and this is 6.3 MPN of E. coli per 100 milliliters. MPN meaning maximum probable number or most probable number. It is a predictive number of how many we would expect to grow had we grown it on an actual petri dish. So we report the results of 6.3 mpn per 100 mils. Now we've done a lot of work, with trying to figure out a better, cheaper, easier way to enumerate E. coli in developing parts of the world. Just this last winter, a few months ago, you can see Nixon Rotich here grabbing water samples. This is from the area that he grew up, and you can even see the banana tree there in the background. And he grew up drinking that water from this stream. And again, we've got the Idexx tray sealer here. You can see the rubber tray insert. He's actually doing some enumeration of some E. coli using the light box there, and we'll talk about that in a second. You can just see this gorgeous view of the Curio Valley. This is like where he grew up at, so he got to see this every morning growing up. So we've got the little cloth here pulled up so you can see what this looks like underneath of this black light. So this long wave UV light is dangerous to your eyes, so you want to have protective goggles or use this UV light box that's got the protective lens here. We've got the cloth pulled up for the picture to show you what it looks like on the inside. Now you'll notice that there's a lot of yellow wells on that plate, and you can see all these yellow wells. This particular sample is good. These have a lot of what are called total coliforms. Now total coliforms are a more general or broad group, if you remember from earlier presentations. Some of the total coliforms are actually the E. coli. The total coliforms are a more general indicator, but they're actually not very predictive of gastrointestinal illness. The E. coli are a much better predictor. So let's look at the E. coli and let's enumerate this sample. So zooming in, here's what we see, and I think the whole thing on there, enough of it. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And then we would also count that one, but we got these two little ones too. So we've got 2 little ones and 21 large ones. So 21 large, 2 small. We go to the MPN table and we're still on the front page. So actually we don't need 21 small. We've got 2 small right here, 2 small. How many large? 21. So let's go to see where the 2 and the 21 cross, and they cross right there at 29.2. So we would report 29.2 mpn per 100 milliliters. That's 29.2 mpn of E. coli per 100 milliliters. There are other tests that are out there, including the presence-absence test. And some of these, they may turn this color, then you put a black light up against them, and then they glow. This was that Canadian company, the Blue Water Biosciences plate. Again, they're not biodegradable. They're $10 a piece. And you can see Peter Sigley, his little brother, and his nephew helping us out. They're all grown up now. It's been 8 years ago. You pour the water into the plate. You incubate it for a day or longer if you need to, if it's not warm enough. And then you shine a black light. This is a battery-operated black light over it to enumerate the E. coli. Down here, this is just a quick image of E. coli method 1603, or EPA method 1603. And it's a petri dish based method that we'll talk more about here in a second. It's not the best method in the world to use because you have to be able to keep the petri dish cold. You're not going to be able to transport it very easily unless you're shipping it cold, because the petri dishes are like Jello. Like, they're not going to do well when it's wet. So, not wet, but they're not going to do well when it gets warmer, because the gel structure to it breaks down and it kind of becomes more like water or like a syrupy. So EPA method 1603, it's that petri dish based method. A person could get their water sample, like a drinking water sample, or they can go out and get their lake water sample from like a beach by going out 3 feet in water, sweeping this under a foot under the surface, and then there's like a little cup that you set on top of this. There's a piece of filter paper there, and you will vacuum the water through here. So you turn on the pump, or you use a hand suction, and you suck the water into this, and the water will go through, but that piece of filter paper it's pretty small in terms of pore space, 0.45 microns in pore space. And that ends up causing the bacteria and anything larger than bacteria to get trapped on the top. And then the water gets sucked through, but the bacteria and anything larger than a bacteria, including algae, they all get trapped on the top of that. We then take that filter off and lay it on a petri dish, and then we have to incubate it for a period of time. In fact, we incubate it for 2 hours at 35 degrees Celsius, which is about 90 something degrees Fahrenheit. And then we incubate for another 22 hours at 44.5 degrees Celsius, which now you're getting up into like somewhere, I don't know, between 125 and 140 degrees Fahrenheit. So you're getting up really, really warm. So like 44.5 degrees Celsius is like, some birds, they're that temperature. So E. coli grow on this method. This is the EPA method 1603, and it's called enumeration of E. coli by membrane filtration with modified thermotolerant E. coli agar. So it's called mTEC, modified thermotolerant E. coli agar. It's special food for the bacteria for you to be able to grow them at these elevated temperatures. By growing them at these elevated temperatures, it deters a lot of other bacteria from trying to grow and compete with what you're trying to count. And we don't want other things competing with the E. coli because we want to be able to clearly see the E. coli growing, and we don't want them to be losing any food to other bacteria. The media, the modified thermotolerant E. coli agar, it also has like bile salts and other stuff in it to create more of like the conditions that are favorable for E. coli and that restrict a lot of other things that wouldn't want to live there. So it really simulates some of the stuff that would be in like a human or a bird or an animal type gut. So we have our cups of water. Usually the protocol calls for filling one up with 100 milliliters. And then you would then later do one with like 50 and another one with 20. You actually probably would do it in the order of 20 first, then you would do the 50, and then you would do the 100. And you would go through the same process. So you've got your cup, you would filter the water through, you would then take your little filter membrane, and you would then lay the filter membrane on your petri dish, put the lid on your petri dish, and then you put it upside down in an incubator, and you wait. After incubation, you get these magenta colored colonies. You can see the one that's the 100 milliliter one. This is like from Lake Riva. You can see the one with the 100 milliliters has a lot of algae behind it. The one with 20 milliliters has less algae kind of in the background. The one that's 100 milliliters, you can also see there's more colonies. The one with 20 milliliters has less colonies. So we filtered 5 times less, or 1/5 the amount of water here. We filtered half the water here. When we do our E. coli counting on these plates, we want to count the magenta colored colonies. So these are colony forming units. And if there's more than 20 to 60, like on that one, you may not worry about counting. But on these ones, they're probably in that 20 to 60 range. So you would want to count them and then do the average or the geometric mean, depending upon the protocol you're choosing to use. Here's just a sample example that I've altered a little bit. So this one, I've got about 68 colony forming units per 100 milliliters. This one, if we count it, there's 44 out of this 50 milliliter filtration. And here there's 23 out of this 20 milliliter filtration. So the 20 mils has the least, 44 has the middle, 68 has the most. Now, sometimes when you're growing these bacteria, just like over here, more will grow per milliliter in the smaller volumes because there's less competition for food. So that makes it easier for the E. coli to get started and survive. That's not always true, but usually that's the case. So let's go to this example. When we report our results, we report our results commensurate with the standards. And the standards are all based upon per 100 milliliters when you look at drinking water as well as recreational water like beaches and pools. So we have to multiply this by nothing because it's already 68 per 100 mils. If we wanted to go from 50 milliliters to 100 milliliters, what would we have to do? We would have to multiply by 2. So that 44 would become what? 88. Now with the 20 milliliter volume, we need to report it per 100 milliliters. So how many times do we have to multiply this by? 100 divided by 20, it's 5 times. So this is 5 times smaller than 100. So we have to scale this up 5 times. So we have to multiply the 23 by 5, and what do we get? So we get 68 for this one because it doesn't change. This one we double, we get 88. We multiply this one by 5, and we get 115. Now, which ones should we count in our average? If you wanted to do all 3 of them, you could. 68 is not an egregious number. But 44 and 23 are definitely in that 20 to 60 range. If you don't have any in that range, you might have to work with what you got. But ideally, CFUs on the plate should be between 20 and 60, so we could average not the 44 and 23. We're going to average the per 100 mil volume. We'll average the 88 and the 115, and when you do that, I don't know, you're looking at around probably a little more than 100 CFUs per 100 mils. Again, these are in CFUs, colony forming units. Now, what do these mean? Like, oh, we found E. coli, so it's horrible, that's awful. Well, there's an infectious disease risk that goes up as the E. coli numbers go up. So the WHO, based out of Geneva, Switzerland, has guidelines or recommendations, and then even the EPA, they've got recommendations through the Clean Water Act for recreational water quality criteria to be set. They also have through the Safe Drinking Water Act requirements for drinking water utilities. The Commonwealth of Kentucky concurs with the US EPA's guidance. So the E. coli densities, according to the World Health Organization, if it's drinking water, says that when you've got 0, that's ideal, but 1 to 10 is low risk. Over 1,000 is very high risk. And I've seen a lot of water samples that have been in that range, and people drink it. And they don't have the ability, to drink out of a tap from a public utility. So their only option is maybe to add chlorine tablets, which cost money and make the water taste like bleach, and produces a lot of disinfection byproducts that they may not know about, but we know are carcinogens. Or what else do they do? Well, they have to boil it. And I know people who don't even want to boil broccoli or boil potatoes because of how long it might take. Could you imagine having to boil your water every day over a fire? You can understand why people probably don't necessarily, boil their water all the time and have to endure through this. So, and then they may have to fetch the water from a distant place. So again, if hard work was all it took in this world to become a millionaire, I know a bunch of African women that would be multimillionaires. So when we look at here in the United States, we say that our beaches, like if you're swimming in lake water, should never be more than 235 CFUs per 100 milliliters during the swimming season. So if it is, there should be an advisory sign posted until the levels get back below that level. So the single day maximum is 235 colony forming units per 100 milliliters. Our water plants, they never want to see E. coli in their water. There's a little bit of a nuance here, but we'll just say for here, 0 E. coli per 100 milliliters. And they pretty much test anywhere between 25 and 30 times per month. Now, that E. coli level for recreation is based upon this. So this is from the recreational water quality criteria that says if there's 235 E. coli per 100 milliliters in the water, that is associated with 36 gastrointestinal illnesses per 1,000 people. And over here, this says that if you chose to use 190 CFUs, if a state wanted to use this, there would be 32 illnesses per 1,000, which would mean that 3.2% of all the people who swam in that water would get sick. As you go up above 235, say you're at 500 or 1,000, You could imagine these numbers would get a lot higher. So, if it's at 1,000, it might be as much as 100 people get sick. And what is the NGI? Those are the gastrointestinal illnesses from what was called the NEAR study. And the NGI, so near gastrointestinal illness, things like vomiting, diarrhea, stomach cramps with a fever, all that kind of stuff. So, for our review, true or false, all bacteria are pathogens. So this should have been a review from before, and we would know that that's false. Most bacteria are really good for us. They digest our food for us. They make our skin soft. So, all right, are E. coli pathogenic? Are all E. coli pathogenic? And we would know that that is false here. Why is it false? Because most E. coli are really good for us in digesting our food. It's a few bad actors here and there. They're the rare ones that are the toxigenic strains, the ones that produce toxins. And sometimes you hear about them when animals like cattle may shed them in their stool or in their manure, and that might run off into fresh produce, and people get sick from eating produce contaminated with pathogenic E. coli, but usually they're not pathogenic. We measure them because they help us know how many other fecal-associated bacteria, including pathogens, may be present. And if fecal bacteria are present, also maybe fecal-associated viruses and parasites may also be present. So we measure E. coli as an indicator. Not because the E. coli are pathogens, but because as their presence or their density in particular increases, the likelihood of an infectious disease increases with exposure. What is the definition of a pathogen? A pathogen is defined as, kind of any infectious agent that causes disease. So it has to make you sick. So it's something that causes disease. It could be a virus, it could be a parasite, it could be, bacteria. What's wrong with E. coli is drafted there? Should be italicized E and should be lowercase c. All this should be italicized. Acronyms, CFUs and MPNs. CFUs are colony forming units. MPNs are maximum probable number or most probable number, depending upon what your source is. The MPN values are based off of the CFUs. So our gold standard is the modified thermotolerant E. coli agar. The MPNs for the Idexx method were compared against that. The MPN is how many would we expect to be colonies growing on a plate from a given sample. So it's those results from those methods like the Colilert method, when you don't actually have colonies, but you're counting like the wells that are glowing. So that wraps everything up. If you have any questions, you can always reach out to me, and I hope that this has been informative. You can see that these environmental microbiology techniques for enumerating E. coli are not all too difficult, and we're planning on we've got a provisional patent on how to make one even better. And if you've got any questions, you can always reach out to me, and you've got my cell, so you can contact me there as well. So I hope this has been helpful, and you have a wonderful rest of your day or evening, depending upon when you're watching this. Bye now.